Yes.
It's really nice to be here, a part of this developmental session. I should admit from the start that I actually have no background at all in developmental science, and this project was a joint project with Kate Hartley's lab, also at NYU, and I learned a lot about development in the process, and I hope to continue that here. This project was led by Ili Ma and Camille Vaneuve, and I'm going to do my best to channel them here. So if any of you has interacted with children or adolescents, you know that planning can be very challenging for them. So if you fail to foresee the consequences of your actions, you might end up with unfortunate haircuts or find yourself in sticky situations. But not all individuals are poor planners. So if you manage to think multiple steps ahead and evaluate the consequences of your actions, then you might make for a very formidable board game opponent, such as the child in this checkers game. Planning is, I'm really sorry, something is going wrong with my screen sharing. I'm going to, I think my PowerPoint just crashed. Okay, let me try that again. Okay, all right. Okay, yeah. Can everyone see the PowerPoint now?
Yes, we can see.
Okay, cool. Yeah, sorry about that. So we're going to play from here. Okay, so and now we're seeing the presenter notes. Yeah. So planning is everywhere because sequential decision making is everywhere. So if you navigate from one place to another place, if you're writing, if you're planning your career, all of those require thinking multiple steps ahead. And in cognitive science is therefore a very interesting question how individuals plan. And much is known about the components that go into planning. So you have to pay attention to the features of a current state, evaluate the current state, think about the states that can arise from your actions, evaluate those actions, and based on that, choose the best course of action. And that brings us to the question of today, which is, does the way that individuals plan change with age? Because all of those component processes, they plausibly have some kind of developmental trajectory. So what's already known about planning across development? So there are many forms of forward thinking that exhibit age-related improvements. For example, there's greater patience in tasks that involve delayed rewards, a greater propensity to imagine future events, during development, during childhood and adolescence. And cognitive processes that play a role in planning demonstrate, show age-related improvements, such as attentional control, working memory, and mental simulation. There have been developmental studies that have used sequential planning tasks, and they also observe age-related improvements. Now, what's missing here still is a characterization of the development of the components of the planning process. So we're going to try to sort of find the components of planning in a novel task here and try to see how those change during childhood and adolescence. So what paradigm are we going to use for that? So there's been a lot of attention to paradigms that go hand in hand with computational modeling, because computational models allow you to potentially separate different component processes. So one very well-known example is the two-step task, which has been used extensively to show that during childhood and adolescence, individuals acquire more model-based reasoning. But the problem with the two-step task is that it's only two steps. So you cannot actually, you actually don't need to think that far ahead. You can exhaustively think through all the possibilities. And that's actually very uncharacteristic for real-world planning processes. So we're looking here for a paradigm that has a little bit more real-world complexity, where you can characterize the depth of planning while still staying within this realm of computationally tractable tasks. And the task that we use for that is 4 in a row, which is a variant of tic-tac-toe. So we've been using this quite extensively in my lab and also in other labs, where the goal is to get 4 in a row horizontally, vertically, or diagonally. So it's just the same idea as in tic-tac-toe. It's different from Connect 4. And this game is quite a bit more complex than tasks that have been previously used in the cognitive science literature. And if you want to see a survey of that, you can look at this review paper. So if you count the number of states in this game, it's 10 to the 16th. And that introduces a level of complexity that, that is high, but at the same time still computationally tractable. Now, if you want to play this game, then you have to evaluate board states. And we're going to do that based on task-relevant features. So the first feature is the centrality feature, which is that if you place your piece near the center of the board, it tends to be better. What you see here is other features which consist of 2 in a row that have the potential to be extended to a 4 in a row. Right? So, for example, 2 black pieces and then 2 empty squares on the right that can be completed to a 4 in a row. So those are 2 kinds of features, connected or unconnected. Then 3 in a row with an empty square on the end is a feature, and 4 in a row itself is a feature. So you end up with an evaluation function that consists of feature counts, fi. I is the feature index, and those are weighted. And those weights are fitted on an individual basis. So you end up with a value that you can assign to a board state. And you calculate that for yourself and for your opponent. So in that way, you're essentially trying to increase the features for yourself and decrease the features for your opponent. Now, this value function is embedded within a tree search algorithm. And that's how we're going to model human play. So this is a schematic diagram of the tree search. Each node is a board position. And in the model, you are evaluating sequences of moves, but not necessarily all to the same depth. First of all, you're pruning candidate actions that have a value that are much lower than the best possible action. You compute the value function with some noise. You make random moves with some small probability. And then you have a search process that terminates randomly with some probability at every iteration, and also when the best option hasn't changed for a while. So this is a very high level description of this model. And finally, and this is going to be important in a bit, the model overlooks a feature on the board with some probability, like what you would typically have if you're playing chess or any other board game. Now, participants in this study range from 8 to 25-year-old, so we had a wide age range. This was conducted online, 156 subjects in total. We also administered the Barrett Impulsiveness Scale and the Future Orientation Scale. The task performance at the highest level can be described through ELO rating. So the ELO rating is how strongly you play. And just this is borrowed from chess. And just to give you an idea of what these numbers mean, if you have a 200 points higher ELO rating than me, you have a 76% chance of winning a game against me. Right? So this is a relative scale. ELO ratings increase with age. The individuals are the symbols here, and the colors are the age groups, children, adolescents, and adults. And this increase parallels the increase in model-based decision-making that has been found using the two-step task in previous work. But now that we have this task and a computational model for this task, we can try to ask what are the component processes that are responsible for this increase in playing strength. We use 3 metrics for that, which are derived from the model that is fitted to individual play. So the metrics are planning depth, which is how many steps you think ahead. Heuristic quality, which is how well does your evaluation of a particular board position correlate with the objective evaluation, like how good position objectively is for the player. And finally, this feature drop rate that I mentioned previously, which is the probability if you overlook a feature somewhere on the board. So we can use these three summary metrics, these model-derived summary metrics to characterize the development of planning. Here's at the top, you see the plot I already showed you, and at the bottom, you see the three metrics. So we see that planning depth increases with age, heuristic quality increases with age, and feature drop rate is not correlated with age. So it doesn't change. So what we find here is that people actually think further ahead as they grow older. Now, we can next ask how informative or how predictive is each of those metrics for individuals' playing strength. So here, again, we've used color to label the different groups, but importantly, in the regressions that I'm going to present, we use age as a continuous regressor. So we're not dividing it into three categories. That's just for the visualization. So what you see here is that the relationship between ELO rating, so playing strength and playing depth, and there's a significant interaction between the two. So that means that in adults, there is actually a stronger relationship between the two quantities than in children. Right? So that means it becomes more predictive, planning that becomes more predictive over age. ELO ratings, it's the same story. So ELO ratings, heuristic quality becomes less predictive of age. So this is a little bit harder to see. The effect sizes are actually quite similar, but there is a significant interaction. And the feature drop rate does not have a significant interaction with age. So it doesn't change there's no evidence that it changes in how predictive it is of playing strength. So we've now shown you the results of these component processes derived from the model, but it's also worth looking at more traditional measures, such as those obtained from self-report questionnaires. So the Barrett Impulsiveness Scale, the BIS brief, includes 8 items that, such as I plan tasks carefully, and we ask subjects to endorse those statements. Future orientation skills includes items such as some people spend very little time thinking about how things might be in the future. And what we find is that these are correlated with age. So older individuals, they think more about the future and make less impulsive decisions according to the BIS brief. However, if you account for age, then neither of these questionnaires is predictive of the model-based metrics from the behavior. So that suggests that potentially these are measuring the behavioral task is measuring different dimensions or different components of planning than those questionnaires. This is coming back to the original question, does the way that individuals plan change with age? So the data that we have suggests the story where as children grow older, they first would refine their heuristic strategies, the quality of their evaluations of board states into early adolescence. And then later, as a secondary improvement in planning, they would actually search deeper and increase the number of states that they would consider. So that would start in later adolescence and going on into adulthood. And that the fact that there are fewer attentional oversights and stronger players is something that's true across ages. So this doesn't just say that planning increases age, but it also gives hints at different time courses for the components of this planning process. And what was quite critical here is that we had this relatively complex task that allows us to do computational modeling and fit to individuals. Of course, we still need to know what drives the maturation of each of those component processes. this is just to show that this 4-in-a-row paradigm has also been used for answering very different questions, and it's a relatively versatile paradigm for studying complex planning. Thanks to the participants, to all the labs, the funding sources, and to you for listening.